Welcome back to the latest lecture session. In the last session, we looked at activated sludge process, relevant variables such as substrate, microbial concentration, and so on and so forth. And we looked at how to design a plant, as in, let's say, if I understand the level of this effluent wastewater strength, let's say, or S effluent that I want, I can design the plant given cell retention time or such. In that context, or I believe in that same session, we also discussed bulking of sludge. And as I mentioned, bulking of sludge, there are various aspects, and depending on which source you look at, there is overlap of some aspects. So let's just take a quick recap of bulking of sludge and then move on to relevant aspects, right? So bulking of sludge, what is it that we have? We have poor settling, right? And why is that? Because of the different kinds of microbes that thrive. The microbes that I want are typically flock forming microbes that have lower surface area per unit mass, let's say, right? But if I have microbes like filamentous microbes which have greater surface area per unit mass, they are not going to settle down. In general, you want to have a good mix, or not good mix, good ratio of filamentous to flock forming, right? If you have just flock forming pin flocks, again that's going to be an issue. If you have too many filamentous microbes due to various conditions, again you are going to have higher surface area per unit mass and they are not going to settle down. A quick recap of what we have been up to. So poor settling characteristics, right? And what is it, where do we typically see that? In the secondary clarifier or the secondary sedimentation tank. And sometimes the situation is so severe that it can overflow, let's say. Again, there are different kinds, but as I mentioned, looks like different sources mix different aspects. One is sludge bulking, and in the way that we looked at it, we encompass most of the kinds of issues with sludge settling within bulking, but different sources distinguish between bulking, right? Viscous bulking, let's say, viscous bulking, and then foaming, right? So let's just have a quick recap of these aspects. So F/M ratio, food to microorganism, and this is from MIT Open Courseware, but the reference they looked at was Reynolds, right? And this seems to be a relatively unique reference in the sense that typically we understand that at low F/M ratio, when the microbes are starving, you typically have filamentous microbes. But here this reference tells us that even at high F/M ratio, right, it does encourage the growth of a certain kind of filamentous microbe that can lead to bulking of sludge. Again, but this seems to be a one-off reference. In general, low F/M ratio leads to filamentous growth, and that will lead to, what do we say, poor settling characteristics, and thus you are going to have higher, what do we say, microbial concentration being suspended in the secondary clarifier. So you are not going to get just treated wastewater, you are also going to get considerable microbial concentration out of your settled sludge, not settled sludge, out of your secondary clarifier, right? If the sludge does not settle down, you are going to have microbes out here and they are going to leave with the water. And the other one is with respect to foaming. So typically nocardia, that causes foaming, right? Here we talked about bulking of sludge and foaming, but typically it leads to foaming. This is the kind, and this seems to be prevalent when we have fine diffusers, or again the conditions are described in different ways and different sources. But one aspect of the principle here seems to be that you have air, right, and nocardia type of microbes which are relatively hydrophobic. Hydrophobic means they don't want to stay in water, so they want to change phase into, or would like to stay in this maybe gaseous bubble, and they will lift up, and this is what you see here. So severe cases, you will have a lot of such nocardia growth, and you will have foaming that's going to go out of your secondary sedimentation tank. And another aspect is, because they are going to stay afloat here, right, they are going to spend more time in the tank, let's see. So that means that these kinds of microbes typically have greater cell resistance time, and so that can lead to some issues, let's say. And again, different kinds, as in long chain fatty acids at low temperature, we discussed this. Another one which is viscous, what do we say, bulking, but which is non-filamentous bulking. Low nutrient concentration, leads to production of bacterial slime, and this slime is remarkably hydrophilic. So you have greater water retention within the cells, and thus, it won't settle down. So that leads to viscous or slime bulking, let's say, right? And let's look at some aspects. This is from Metcalfe and Eddy out here, right? As I mentioned, different sources, different aspects, but there are some aspects where, more or less there is considerable agreement. So here we are looking at causes of filament growth. So most often we look at low F by M, right? Pretty low F by M. That leads to the formation of a kind of filaments or filament bacteria, right? And then low DO, typically 0.5 milligrams or so, right? In such cases also you will see kind of filamentous growth. And again, low F by M and thus and also completely mixed reactor conditions. That's what will typically lead to low F by M, right? When do you want to have low F, right? When your effluent quality is to be low. Effluent quality low meaning our waste in that effluent has to be low, meaning low food for the relevant microbes, especially if it's a continuously stirred tank reactor, right? If it's continuously stirred, whatever has to go out will be the same concentration within. So if I have low F by M because I want to have low waste, or let's say 10 milligram per liter BOD in my effluent, right? So, well, again, this is an extreme case. So obviously I'll have low F by M in my completely mixed reactor system. And another case is when we have sulfide content or sulfide available and some septic wastewater coming in, let's say at different times of the day, then you can have a different kind of filament growth. And nutrient deficiency again leads to a different kind of filament. Again, nutrient deficiency, when will you see that? Typically in industrial wastewaters where there is not enough nitrogen, let's say, right? And that's one case typically indicative of industrial wastewaters. Then you might need to add nitrogen. Low pH, you have fungi, right? They predominate in typical conditions. Fungi can't predominate, but in conditions where the pH is 6.5 or so, bacteria are less affected, or more affected than fungi, and so fungi can predominate and such. But in sewage, right, or human sewage treatment plants, you typically don't come across this condition. That can be a case when we are looking at industrial wastewaters. So as you see, different kinds of, what do we say, bacteria can thrive depending upon the different conditions, different kinds of filamentous bacteria. So before we go about rectifying an issue, in general, it would always be good to identify the kind of bacteria that's thriving in that, what do we say, sludge which is bulking or which is not settling down, and then try to, what do we say, rectify the scenario. If not, obviously, you can, what do we say, misdiagnose the issue and thus exacerbate the problem. So that's one aspect. And I guess here we have one decent figure again from Metcalfe and Eddy. I think we saw some equation earlier where we had, I think KD here, but let me not go into that. Efficiency and F by M and other variables here, I guess, right? So higher F by M means lower theta C, right? High F by M means low cell retention time. So as we discussed, if the cell retention time is pretty high, let's say, right? Again, you are going to have a different kind of flock. So again, you don't want to have very high or very low, what is it now, SRT or F by M, right? You have a specific range because you want to more or less have a certain kind of filamentous microbes and also considerable ratio of the flock forming microbes, let's say. So that's something to keep in mind, right? So let's move on. Okay, so some pictures again, non-filamentous, good settling flock, but again here there are relatively less, filamentous microbes, but in general we don't want flocks, only flock forming, microbes thriving. Why is that? Because if it's the small flock or pin flock, they won't settle. But again, there are some, what do we say, flocks that can settle even in the absence of or complete absence of filamentous growth. And then this is what I guess you typically see. You have some filamentous microbes and you have the flock forming microbes in the relevant proportion or ratio, let's say. Filamentous and I guess flock forming, let's say. So these flocks act as bridges or sometimes as the backbone, and thus you have good settling characteristics. Flock particles with limited filamentous growth, which is what we want, right? And here I guess we have excessive filamentous growth, the filaments extending from flocks causing poor settling characteristics. Again, why don't they settle well? With respect to filaments, as you can see, greater surface area per unit mass, and thus they won't settle down easily. So when we have sulfide, let's say, I guess the kind of filaments that you have, again, please note that the organic content will be decreased in the aeration tank or such, because both the filamentous and the flock forming microbes will degrade it. But in the secondary settling tank, we will not be able to separate the water from the microbes, and again that does not serve our purpose. That is what we need to consider. And under low DO conditions, again a different kind of, what do we say, filamentous microbes thriving, right? So let us move on. Okay, we looked at these aspects, yes, design, we looked at that. We will look at a sample example later, and approaches and such. Now let us look at some of the variations of activated sludge process. In India, a lot of people or many plants typically use only activated sludge process. Only now, I guess, are people moving on to, or more open to looking at variations of activated sludge process to suit their needs. We will not go into detail because this is a UG class, right? Again, there are different variations by SRT, let's say, extended aeration. So the key is in extended aeration. So typically low F/m, okay, and with respect to low incoming load. And also the key aspect, as we mentioned, was with respect to SRT. Solid retention time or cell retention time can be around 20 days, while for typical or the usual ASP process, it will be around 5 days, let's say. So you can see that SRT is, or the cells or microbes are spending more time in the relevant system. Again, extended aeration, and thus obviously low F/m. Again, we are not going into that in detail, let's say. So by the kind of mixing, conventional type where you want to more or less try to achieve plug flow, but you can't achieve ideal plug flow, completely mixed, but again this will have its own issues, and step aeration, let's say, right. So this is sometimes practiced, but we won't go into that in detail. Only aspect that we need to know is the kind of mixing and the kind of aeration we are providing will depend upon the kind of system that we are trying to promote, let's say, right. Let us move on. Okay, another variation which is used because it leads to remarkably good effluent water quality is the MBR system, which is the membrane biological reactor. So in general, what do we have? We have this aeration tank where we supply air and mixing, right. And then we have the secondary settling tank where the microbes settle down to the bottom, and this relatively clear water is removed, let's say, yes. So this replaces the settler, right, and this meaning the membrane filters replace the settler. So you have different types: internal, immersed in aeration basin, vacuum, and depending on whether we are applying the pressure or is it by gravity and such, right. Let's see what we have. So why do we want it first? Obviously because the quality of the effluent is high. These membranes, which can be nano or ultra filtration membranes, will not let the microbes pass through the membrane, and thus you will only have water or relatively clear water free of most suspended solids passing through this MBR, and then that is going to leave the system. That is your treated wastewater, and the microbes are going to stay in the system itself, right. So high quality effluent, relatively reliable, and low microorganism concentrations because you are not really wasting them, they are staying in the system. But obviously, compared to what do we say, the conventional ASP process, MBR is relatively more expensive depending upon the maintenance of MBR. You can have fouling of the membranes, right? Over time, you are going to have fouling, as in you have these nano, membranes or ultrafiltration membranes. Size of the pores is very less. Due to different kinds of either precipitation or microbial growth, you are going to have fouling, as in not enough pore space, if I may say so, or pore area for the water to go through, right? And thus you are going to have to apply pressure, which again means higher cost or less flow rate. So maintenance is an issue depending on how well you are running the plant. But one other aspect which I should have mentioned here is that it requires lesser area when compared to the traditional ASP process. Why is that? As in, why do we need lesser area? Well, I guess it was obvious. We have the aeration tank and then the secondary settling tank. Right here, we don't need the secondary settling tank, we just need the membranes here. These membranes can also be placed within the aeration tank itself. So that's another advantage depending upon the kind of system that you are going for. So usually it has, let's say, or the area requirements are up to 60% lesser compared to the ASP. So typical MBR membrane biological reactor modules, right? Membrane modules, this is what they look like. So the water has to pass through these, let's say this is a kind of MBR or membrane. We have the hollow fiber. The water has to pass through these fibers, yes, that you can see out here. This is a hollow fiber, let's say, right? And what do we have? Membrane module, which is to be installed in a rack or cassette, and an individual hollow fiber. And one other aspect is sometimes you will also have attached growth, not only suspended growth, but again that varies depending on the kind of system that you want to have. Here you see these membranes being lowered into the relevant tank. Again, as we mentioned, the water will flow around it and then will have to flow through this membrane. Thus, the microbes will not be able to pass through the membrane and the clear water will move out of the system, let's say, right? Let's move on. So, air bubbles in an MBR, as you can see, model MBR where you have the membranes and the aeration occurring together. Again, different kinds of aeration, let's see. So, we talked about different kinds of aeration or activated sludge process, but one that's pretty widely used or very much coming up within the, at least within India, is the sequential batch reactor. Sequential batch reactor, right? Why? If the first case, efficiency will be greater, because if we look at the way that it's going to be run or operated, you will see that the rates are going to be similar to what you would expect in a not completely mixed, in a plug flow system. And also you will see that the area requirements are much lesser, let's see. So let's see, or let's try to understand how the biological process are taken care of within this batch reactor. When we say batch reactor, what does it mean? There is no continuous flow coming in, no continuous flow going out. So what's going to happen? Or how do we, treat the continuous flow coming in from the distribution network or sewerage network, pardon me. So you typically have more than one SBR, sequential batch reactors, at a minimum of 2, if not more, let's see. And then you can have an equalization tank, and then you will have bioselectors depending on how advanced it is, but we will discuss that later. So this tank will be in a different cycle, tank 1, and this tank will be in a different cycle. So we will look at the case where we have 2 tanks, because we will be looking at a video of a sewage treatment plant in IIT Roorkee that's based on SBR, sequential batch reactor. So let's try to understand the system and then move on to looking at the relevant video, right? So what is it that we have? First, the wastewater is coming in, right? So you have filling here, right? You have filling, and then after the tank is full, or depending upon the relevant scenario, what do you have? You are going to have aeration, let's say. Aeration, where you are going to provide the relevant oxygen for the microbes to degrade your waste. So one aspect during aeration is that, unlike the completely mixed system, note that this is a batch system. Once it is filled, there is no more inflow, right? So now we have wastewater at, let's say, 150 milligram per liter, and the rate of this substrate utilization or the rate of degradation of the microbes will certainly be not microbes. Rate of degradation of our waste will be depend upon the strength of the wastewater. So let's say it's going to be depend upon the concentration. Over time, this 150 will keep coming down, 100, 70 or 20 or so on and so forth. So rate will come down, but if we look at the R average, it's certainly going to be much better than a completely mixed system, which will always try to maintain a much lower concentration inside the system. Let's see. Again, that's one aspect to keep in mind. So first, what do we have? We are filling the tank, and then we have the aeration, and then you will have the settling, as in when you will stop the air. If you have continuous aeration, obviously you are going to have turbulence. The flocks that have formed or the kind of microbes that have formed will not be able to settle down. So you will want to have stop aeration and have settling, let's say, right? And after these microbes have settled down, let's say, you want to remove the clear water from the top. So that is called decanting. So after decanting, now the tank is again empty. So what's going to happen? The next batch of wastewater is going to come in, as in you are again going to have a new set of wastewater coming into the tank, which is filling, again aeration, again settling, again decanting, and then again the cycle repeats. So these are the 4 cycles. So some aspects that we need to discuss before we go ahead and look at the video is that with respect to aeration, I know that we haven't yet talked about nitrogen removal or such in great detail, but we know that for nitrification and denitrification to occur, again, at least at some conditions, you want to have anoxic conditions, and even for phosphorus removal, you will have certain conditions that need to be maintained. So in SBR, you have greater control about the kind of aeration and also the level of aeration that you want to achieve or can achieve, and thus you can achieve nutrient removal during SBR process. Again, we'll look at that later, but this is something that we are going to look at it in a video, let's say, right? So, but I see that I'm almost out of time. I will end this session for today. In the next session, we are going to look at the SBR system or process or the SBR sewage treatment plant at IIT Roorkee. Again, the crux of the issue is you are going to fill up this batch reactor, meaning no flow coming in, no flow going out. And after you fill it up, you are going to pump air in, aeration. And then after the relevant time which you design, you are going to stop this aeration. And then you are going to let the plant, the reactor have quiescent conditions such that it settles down, and then you are going to decant the clear water, right? So with that, I will end today's session. Thank you.